In this video, I want to go back and take a look at some of the models that we investigated back in Chapter 1 and talk about actual methods for solving the equations that came up from those models. So basically, we've built up a stable of tools that we can use to try to solve first-order differential equations. Let's go back and look at a bunch of the models that were designed as first-order differential equations and actually solve them. The first one I want to look at is going to be Newton's law of cooling. So let's solve some of our older models. And again, the first example I want to look at is the Newton's law of cooling example. So if you'll recall, Newton's law of cooling led us to an equation, a differential equation that looked like the following, dt dt. So the capital T represented temperature, the lowercase t represented time, dt dt equals k times t minus tm, with presumably some initial condition that we might have that maybe t at time 0 is equal to some value t0. So in this model, we also had that the value of k had to be negative to ensure that basically when we had a hot temperature relative to the room temperature that it would cool off, and when we had a cold object relative to the room temperature that it would heat up to that room temperature. So this is the idea. This was our model. We derived it in detail back in section 1.3, I think. So let's solve this now. You'll notice this is a linear equation. It's linear in the dependent variable t, so we could solve it using an integrating factor. And it's also possible to separate this one. So we're going to have two different approaches. So two possibilities. Two possibilities. In the first possibility, I'm going to rearrange this to be in the same form that we used integrating factor on. So in that case, we did dt dt and made sure that this coefficient was 1, which is nice, it already is. And we moved the other factor with a t over to the left-hand side as well. So this would be minus kt equals whatever's left over on the right-hand side, which would be the k times this negative tm term. So we'd have this term remaining on the right-hand side, and it would look like negative k tm. So that is one that we could use integrating factor. So linear, use integrating factor. Or we could separate it. And if I come back over here to separate it, the easiest way to do it is basically just multiply both sides by dt to move the lowercase t term onto the right, and then divide by the stuff in the parentheses to move the capital T over to the left. So if I did that, our second possibility is we could rearrange this equation to look like dt over t minus tm is equal to, on the right-hand side, we would have k, and we would have the lowercase dt show up on the right-hand side. So again, that's just multiplying both sides by lowercase dt and dividing by the stuff in the parentheses will lead to this. And so this is clear that it is also separable. So you can use either approach, whichever one you are more comfortable with to solve this. You could use integrating factor on this form of the on this rearrangement of the terms in the equation, or you could use the separable approach on this rearrangement of terms. It's kind of up to us. I think I'm going to go with the separable approach. So if we're doing the separable approach, all that I'll need to do is integrate both the left and right-hand sides. And when we do that, on the left-hand side, we would have to do a small u substitution. We would basically have to replace the denominator here, call the whole denominator u, and we could write this as du over u, but we will get natural log of the absolute value of t minus tm. So this would be the result that we would get doing u substitution. If you want to do that aside, you can do that on your own. And on the other side, we have this k times dt term, which will lead to kt, and we'll say call it plus some constant. So we'll call this plus c1. And just real quickly, just for people that aren't, super quick with their integration, here's how I would do this side if we wanted to do it over here. Basically, I'd just say let u be equal to t minus tm. What will du be if I take the derivative? Du is going to be the same as capital DT, and all we have over here is literally du, which is the capital DT, over t minus tm, which is u. So this is just du over u, which would give us the natural log of the absolute value of u. And we would convert back to the original variable t, and we would get what we've got right here. Okay, so the next step is, if at all possible, solve for t. The first thing I want to do is unwind this natural log. So how do we undo a natural log? I'm going to exponentiate both sides. And so we'll have e to the natural log of the absolute value of t minus tm on the left-hand side, and I will have e to the kt plus c1 on the right-hand side. On the left-hand side, the e and the natural log will cancel, and I'll just be left with absolute value of t minus tm. And on the right-hand side, I'm going to have this exponential, and we can think of the plus c1 term, the e to the raised to that, as being basically just another constant that I'll call c2, e to the kt. And just note that c2 is equal to e to the c1. So some new constant that we've got there. At this point, we know that basically over here, the way that we've got this set up based on the arguments, this came from an exponential. This e to the c1 term is also presumably, or is also an exponential. So that means that this term has to be positive. The whole thing over here has to be positive. We can drop the absolute values. We wind up with t minus tm equals c2 e to the kt. And the last thing that we do is add tm to both sides to wind up with t equals tm plus c2 e to the kt. And so that is what our equation winds up looking like. This is the solution. If we wanted to come back and plug in our initial condition that's written up here, we could actually solve for basically one of these variables here. We could solve for what C2 is. So we can do that if we want. It's not too bad. So plug in the initial condition that t of 0 is equal to some new parameter that we're just calling t naught. So it's just some number. So if I plug that in, I know that at time 0 on the left-hand side, I'll get t naught, and on the right-hand side, I'll get tm plus c2 e to the k times 0. But what is e to the k times 0? Well, k times 0 is just 0. E to that 0 is just going to be 1. And I just get t0 equals tm plus c2. So what does that mean that c2 must be? Well, all I need to do is subtract tm from both sides, and we'll get t0 minus tm. So the full solution is that t is equal to tm plus c2, but we just found c2 is this term right here, so plus t0 minus tm times e to the kt. And there's what the solution looks like. Okay, we can plug in actual numbers instead of all of these parameters that make things a little bit more abstract. Instead of having this unknown value of k, and this unknown value t naught, and this unknown value tm. Let's do it with some actual numbers and see how we can actually back out some of the values that show up in the equation, given some more kind of reasonable information. So let me give you this example. In this example, I want to say that our room temperature is going to be 80 degrees. So if Tm equals 80 degrees Fahrenheit, that's our room temperature, warm room, and the cake coming out of the oven comes out of the oven at 350 degrees. So presumably, if it comes out of the oven at 350 degrees, what we're presuming is that when it comes out of the oven is kind of when we're going to start our timer. So this is the time that we're going to call T0. 10 minutes later, so let's say after 10 minutes, the cake has cooled to, let's say, 150 degrees. Okay. Let's find an equation for the temperature as a function of time. Okay, so I'm going to go through, just to practice everything, I'm going to go through this procedure from the beginning with the relevant values plugged in to the initial equation. So we're going to set up the equation and actually solve it again, as opposed to just taking this generic solution that we have and just trying to plug numbers in. And that's how I'd recommend you guys do this in general as well. I'm not looking for you to memorize forms of solutions and be able to plug stuff in. I'm looking for you to be able to go through the process of solving these things. So the information that we have available is basically we're starting with dt equals k times t minus tm. Notice that tm is the only parameter in the problem that was actually given. They never gave us k. K, we said, is related, is basically related to the thermal conductivity of the object that's heating up or cooling off here, basically how fast it gains or loses heat. And we have some information that could maybe eventually lead us to finding that value of k, the stuff saying that it came out at 350 degrees at time 0, and then later it's down to 150 degrees after 10 minutes. But we aren't actually given a value for k. The only value we're given in the original equation is this Tm value of 80 degrees. So that's going to be the only number that I plug in. Notice that when we solve this, we will have this parameter k that needs to be determined in order to get our solution. And if we come back and compare to the solution we found generically a minute ago, that's clear. We'll need to know what k is. But we'll also need to know what this constant out in front is, right? We also introduced a constant of integration. One of our conditions, say the initial condition, that the temperature of the cake at time 0 is 350 degrees, that'll be enough to give us our initial condition, which will be enough to give us this constant C2, the value of that, as you can see here. It'll give us this, but it's not enough to give us k. And to solve for k, the remaining parameter that we need to solve for, we'll need an additional piece of information. All I'm trying to say is, for every unknown either parameter or constant of integration that's going to show up, we're going to need one condition to solve for that piece of information. So one condition, one piece of information per unknown that we're trying to find. And because we're going to have our unknown value k plus a constant of integration, we need two different conditions given. And indeed, that's what we're given. We're given an initial condition, and then we're also given a condition 10 minutes later. So that should be enough to solve those two pieces of information, should be enough to solve for our two constants. So let's go ahead and do this. We've already gone through this procedure. We said we could do it with integrating factor. We could do it as a separable equation. Maybe just for practice, we could do this approach this time with integrating factor instead. So I'll rearrange this as an integrating factor problem, which is minus kt, and that's going to be equal to, what are we going to get here? Negative 80k. So here's the rearrangement that will allow us to do integrating factor. So our integrating factor is going to be mu, in this case of t, mu is a function of time, and it's going to be e to the integral of whatever the coefficient is sitting here in front of the t term, the capital T term. So in this case, negative k dt. And so what does our integrating factor wind up being? E to the negative k t. So there's our integrating factor. And that tells me if I multiply the entire equation by that integrating factor, I will get the left-hand side to show up and appear as basically the result of taking product rule of two functions. So I'll have e to the negative kt times dt minus k e to the negative kt times t equals negative 80k times that same integrating factor, negative k e to the negative kt. So I've just multiplied all three terms in the original equation by e to the negative kt. But now I've got it set up that this is the result of product rule. If you think of this as being d dt of t times, in fact, let's write it in the other order, maybe it'd be a little more clear, e to the negative kt times capital T, this is the result of taking that product rule. So when we take the derivative, you'd get first times the derivative of the second. Here's the first times the derivative of the second, plus the second times the derivative of the first. And here's the second. And what is the derivative of e to the negative kt? Well, you'll get back an e to the negative kt, and then by chain rule, you'll also pick up another factor of negative k that we've got sitting right here. So indeed, this left-hand side matches this left-hand side. I haven't touched the right-hand side yet, so it's negative 80k e to the negative kt. We'll integrate both sides with respect to lowercase t. And on the left, the integral and the derivative cancel. We're just left with e to the negative kt times capital T. And on the right-hand side, we have to integrate this term yet again. So I'm going to pull out the negative, I'm going to pull out the 80. Let's just write the 80. And we've got the integral of negative k e to the negative kt dt. I'm intentionally leaving the negative k in here, and hopefully you can start to see why. But if not, the idea is when I do one of these, so you're welcome to, again, do a u substitution if you'd like. You could replace negative kt, call that u, and figure out what your du is. It'll be negative k dt. Or alternatively, I can just know that when I integrate e to the negative kt, I'm going to get something that looks like e to the negative kt again, right? Exponentials integrate to those same exponentials, but there'll be some modifying factor out in front of everything. So if I had something, some e to the negative kt, and I took the derivative to get back to this, what would it have to look like to get this as the derivative? What function would give this as the derivative? So I think of it more of as an antiderivative. So in this case, if I just took the derivative of e to the negative kt, I would pick up this factor of negative k. And so that's enough to tell me that this piece, this integral, is going to be 80 times simply e to the negative kt. Or again, you can also just do a u sub, let u be equal to negative kt. What is du then? It's going to be negative k dt, which is why, again, I left the negative k here. So here's my du term, this piece combined with this piece, and here is my u term. So there's integral of u du, and that's all we need to do, or sorry, e to the u du, e to the u du. What's the integral of e to the u du? It's going to be just e to the u. And sure enough, that's what we get out of all of this. So Just to put you in the mindset of how I'm doing some of these integrals so quickly, again, I usually often on these ones that kind of are simpler, once you've done them enough times, you can kind of spot, oh, I know it's going to be an exponential. Let's just figure out what the appropriate coefficient would be. In this case, it's just a coefficient of 1 that would wind up with this factor of negative k after I took the derivative to get back what's in the integrand here. Okay, hopefully that didn't make things more confusing. So here we go, and the one thing I missed is I also need to get, again, my plus c. And we can call it whatever, plus c1, plus c2, doesn't really matter. And at this point, to solve for t, all I need to do is get rid of the e to the negative kt. And again, instead of dividing by e to the negative kt, I'm just going to multiply by e to the positive kt to cancel these out, and hopefully not make any algebra mistakes like I did in one of the previous videos. So by multiplying by e to the positive kt, the e to the positive kt will cancel out with this term and leave me with a 1. It'll cancel out with this term and leave me with just an 80. And this term will be plus c1 e to the positive kt. And sure enough, we get a solution that looks an awful lot like what we wound up with right here. The only difference being we've prescribed what Tm was. The room temperature was 80 degrees. So we've got something that looks exactly like what we have right here. Now we're going to plug in our initial condition in order to solve for one of these two remaining parameters. So we have two unknown parameters. We have C1 and we have K. We need to figure out both of those two parameters to get the full equation that we're going for, T of T. One of them we can find by using the initial condition. So T0 equals 350 degrees. And then the second we'll find by using the second condition that says that after 10 minutes, the cake has cooled down to 150 degrees. So we'll use the initial condition. The initial condition will give us this value C1. And then we'll use the second condition after 10 minutes, and that'll be enough to give us the value of K. So plug in the various conditions that are given in the problem, that additional information, to solve for C1 and K. So one of them was that basically T of 0 was equal to 350 degrees Fahrenheit. So at time 0, we get 350 degrees. So that tells me on the right, I'm going to have 350 degrees, and that's equal to 80 plus C1 times e to the k times 0. All I've done is plug in time 0 for t, 350 for the capital T. And that gives us this equation. Same arguments as before. E to the k times 0 is just going to be 1. I've got c plus 80, or in this case c1 plus 80 is equal to 350 degrees. So 350 equals 80 plus c1. And what does that mean that our constant c1 has to be? Well, I just subtract 80 from both sides, and I will get what? 270? 270 degrees Fahrenheit. So that's going to be the number that goes there. So we now have that T is equal to 80 plus 270 times e to the kt, because we've found C1. So we've been able to plug in for C1 now. Now we'll use the remaining condition to solve for K. The remaining condition says that T of time 10 is equal to 150 degrees Fahrenheit. And this tells me that when I plug that in, so I'll get a 150 on the left-hand side, is what we get after 80 plus 270 e to the k times 10 for 10 minutes in. And here's our equation. And again, the only unknown is k, so we just need to do some algebra to solve for k. It's not very nice algebra, it's kind of ugly algebra, but it's not going to be the end of the world. So let's try to isolate k by itself. First, let's get rid of this 80. Let's move the 80 over to the other side. So I'm going to subtract 80 degrees from both sides. That'll leave me with 70 degrees on the left. It's equal to 270 e to the, right, this is 10k. Let's get rid of the 270, so divide both sides by 270. I'll have 70 over 270 equals e to the 10k. Let's get rid of the exponential, so let's get rid of the e. To do that, I need to take the natural log of both sides. The natural log of 70 over 270, and obviously we can simplify that fraction if we need to, but for now I'll just leave it. Natural log of 70 over 270 is going to be equal to, what happens when I take the natural log of the right-hand side? I'll simply get 10k, and to solve for k, the last step is to divide by 10. So I'll get the natural log of 70 over 270, whole thing divided by 10. And there's some big, ugly number. We could plug it into a calculator if we wanted. I think I've got to bring up a graphing calculator here. Let's just see what that looks like. So let me clear it, and we can just get an estimate. But one thing we should expect, going way back to the initial setup of this problem, way back, was we have this condition. K needs to be negative, again, in order for hot things to cool off and cool things to heat up. So this better give us a negative number. And if we think about what the natural log function looks like, it goes basically like this, and it passes through this point right here at a coordinate of 1, 0. Basically, if you take the natural log of anything less than 1, you do indeed get negative values. And this number here is positive, but less than 1. So we should wind up getting a negative result out of this. So let's check it out and see what we get. We'll do the natural log of, again, 70 divided by 270. Least we could do is probably cancel those zeros at least. And then divide that whole result by 10, and we should get a negative number here. So this is about negative 0.135-ish, if we round to 3 decimals. So there's our result. I'm going to keep my result exact. I'm not going to put this rounded number in. I'm just going to use this value of k. But for our final answer, we get that t as a function of t is equal to, coming back up to all the information that we had. Here was the last step that we had, and now here's the value of k we need to plug in there. So it's going to be 80 plus 270e to the k, which is now this big ugly mess, natural log of 70 over 270 over 10 times t. And here's our big ugly mess of a result. But that's it. That's our solution. And again, on the real exam, maybe just cancel the zeros, but I would give you full credit for an answer that looked like this. But keep it exact unless I ask you to round. Don't put in the decimal. And just stick to this. Okie doke, so this is the solution. And we've done it, again, 2 ways. We solved it sort of generically using the fact that it's a separable equation, and then we also solved it with these specific values using an integrating factor. Let me minimize this, go back to here, and let's take a look at the next problem. Let's do one of the population growth problems that we did. So you'll recall we actually looked at 2 different population growth models. The simpler one looked like the following. It was dp dt was equal to k times p, or r times p. I think the book might use, maybe they used r here. So let me use r here instead. I think the book used r times p. Okay. In this case, r is just some growth rate of some sort, and we'd have some sort of initial population given at time 0. So let's just, for the sake of argument, let's just say that for us, r is equal to 3, with whatever that happens to look like, and an initial condition that p of 0 is equal to 10. If I didn't give you this value r equals 3, but instead told you what the population was at time 0, and then again told you what the population was at a later point in time, you would go through a technique very similar to what we did up here. So here I've given the value of r. explicitly. I've just said, let's just use 3 for this value. And that means after we solve this differential equation, we'll only have one unknown constant, the constant of integration. But if instead I just left it as dp dt equals r times p, and I gave you an initial condition, I would also need to give you a condition sometime later, maybe, depending on if we're talking about bacteria or rabbits or people, maybe it's a few minutes later, a few hours later, or a few decades later. And we would need 2 separate conditions to solve for both the value of r, this parameter that would be unknown if I hadn't specified it, and then also the constant of integration that we will get when we solve the whole thing. So keep that in mind. In this case, because I'm giving us the value of r, we're only going to have one unknown constant, and so one condition is enough. But if r was not specified in the problem, you would need 2 conditions given. One to solve for r, one to solve for the constant of integration that we're going to get. This one is also very, very straightforward. It is also linear. It is also separable. So let's just do one. I don't want to do both every single time. Let's treat this one as a separable equation. So dp over p equals r times dt. So divided both sides by the p, multiplied by both sides by dt to get a separable equation. And now we're going to integrate both sides. So I should just say again though, this is separable. It is also linear. So we have multiple approaches again that can work on it. But in general, this will not always be true. Not every linear equation is also separable. It just tends to be that all of the homogeneous equations, where t does not show up explicitly in this equation anywhere, those are going to all be separable. So keep that in mind. Okay, so we've got our integral set up. Just integrate both sides. On the left, we're going to get the natural log of the absolute value of p. On the right, we are going to get what's the integral of r dt. That's going to just simply be rt plus some constant. We'll call it c1. Same argument as before. Let's get rid of the natural log. So I'm going to do e to both sides. E to the natural log of the absolute value of p is going to be e to the rt plus c1. On the left-hand side, that'll leave us with the absolute value of p. On the right-hand side, we can rewrite this as some new constant c2 times e to the rt. The argument over here is, again, the exponential is always going to be non-negative. And this constant that we got was technically e to up raised to a constant. So this has to be positive as well, and we can ignore the absolute values and simply write p equals c2 e to the rt. So there is our generic solution. Notice I did this. I forgot to actually plug in the value r equals 3. We otherwise would have just had a 3 sitting here in place of r in all these steps. So we can do that now. So you could have done it back at the beginning. We are doing it now because I forgot to do it at the beginning. So plug in r equals 3. And we will get that p is equal to c2 e to the 3t. And sure enough, we only have one unknown constant. And that can be found using our one condition that's been given. So using our initial condition, plug in the initial condition to find what we're calling C2. So I know that at time 0, the initial population was 10. So p of 0 equals 10 is going to imply that when I plug in t equals 0, the value of p should be 10. So I've got 10 equals c2 e to the 3 times 0. Well, what is e to the 3 times 0? It is going to be 1, right? E to the 0th power is just 1. And that tells me that c2 is 10. And so our solution is that p of t is equal to 10 times e to the 3t. So there is our solution. Do keep in mind what the units of these various pieces represent. If you go back to, if you want to actually apply this solution to find populations, what you'll see is basically keeping in mind what the units of r are. On the left-hand side here, we have dp dt. That means population over time. That means the units on the right have to also be population over time. Well, we have population taken care of by this p here, but we don't have the over time unless we recognize that the growth rate, r, must have units of over time, inverse time, so 1 over t. And we can come back down and do all of this. If this has units of 1 over t, and we're multiplying it by a time t, this whole thing is unitless. This term is unitless. But what were the units of our C2 of this? Well, it was an initial condition that gave us specifically the initial population. The population was 10 at time 0. So this 10 is what has units of population. This piece is unitless. The whole thing has units of p, which is exactly what we're hoping for. So just keep that in mind. And what we see is, in cases like this, we get exponential growth. Right? So this population growth model leads to exponential growth. We've already said that's not going to be very realistic because eventually with exponential growth, you run into environmental limiting factors. You run out of resources. So we'll talk about the other model, the Verhulst model, that took some of those limiting factors into account, but that is a nonlinear model. And so we're not going to focus on that one here. The nonlinear models will come in our next section in the next video. Okay, so we've got Newton's law of cooling done. We've got this simple population growth model done. What's next? Let's do one of the mixing problems. So we also did, back when we talked about our models, we talked about mixing. So chemical mixing and such. Putting a brine solution into a tank and pumping more water into it and seeing what happens. So let me give you a setup. Instead of giving you the big, long word problem, let me just kind of give you re-go over some of the basics here. So let's imagine that we've got a tank. And that tank is filled, in this case, with 200 gallons. So V, the volume, is going to be 200 gallons. And we've got stuff coming into the tank. And maybe over here, what's coming in is coming in at a rate that I'm going to call R in. So the rate that it's coming in is going to be 10 gallons per minute. And maybe what's coming in is pure water. So in this case, the concentration of what's coming in is 0. So what are the units of concentration? 0 pounds per gallon. And maybe the pounds we're talking about are pounds of salt or pounds of sugar being dissolved into this. And then the tank is being mixed and drained, so stuff is coming out of the tank from the bottom. And let's say in this case, the rate that it's coming out is also going to be 10 gallons per minute, which is nice because that means the volume of our tank, the 200 gallons of liquid that are in the tank, that's unchanging because we're pumping the same amount in as we're pumping out. The concentration of what's coming out is unknown. We don't know the concentration out because let's say that the initial concentration in the tank was, so the concentration, initial concentration, was, not even concentration, let's just say initially there were 50 pounds. Let's say initial amount. 50 pounds of salt mixed into that 200 gallons. Okay, so we want to know what is the amount of salt in the tank at time t. So I'm going to call this amount A, and the information we know is related to the rate of change of A. So we have information about dA dt. The amount of salt in the tank as a function of time isn't known directly, but we do know some information about the rate at which that amount is changing. Right? So it initially starts with 50 pounds of salt in here, and we're pumping in pure water and then pumping out a mixed solution of the salt and the water. Big picture, forget the math. What do we expect to have happen over time if we're pumping pure water into this tank? Hopefully it makes sense that eventually we would expect what's left in the tank to essentially be pure water. All of the salt should eventually get washed out because we're pumping in pure water into this tank. So I would expect dA dt, the rate of change of the amount of salt in the tank, I would expect this to be negative eventually. So let's think about what is the amount coming into the tank? How can I get and let's keep in mind the units of here. So what are the units of dA dt? So A is the amount of salt. We're measuring that in pounds. And then T is going to be measured in minutes according to this. So this is pounds per minute. And that tells me everything on this side needs to have those same units. If I multiply the rate in times the concentration that is coming in, so this times this, I have gallons per minute times pounds per gallon. The gallon in the numerator here will cancel with the gallons in the denominator here, and I'll be left with pounds in the numerator, minutes in the denominator, which is exactly what we're going for. So if I just write this as the rate in times the concentration in, minus the rate out times the concentration out, we will wind up with the correct units. The nice thing is, over here, the concentration of what was coming in was 0. So this term, right, and so let's just keep track of the units here. The rate in was gallons per minute. This was pounds per gallon. But this whole thing is going to be 0 because even though the R value was 10, we were multiplying it by the value of C in, which was 0. So this whole term is going to be 0. On the other hand, the rate out, which again has units of gallons per minute, is 10. And the concentration of what's coming out is unknown. But we can figure out how to write it as a concentration by however much is in the tank. So however much salt is in the tank, we know that that's out of 200 total gallons of volume in the tank, that the volume of this tank is not changing. So the concentration is going to have units of basically amount, so it needs to be pounds per gallon. The gallon is the volume of the tank, and this, the pounds, is the amount of salt in the tank. So it's simply going to be A over V. And what is our V? 200. So here's our setup. So our equation in this case, after all that setup, is that we've got dA dt is going to be 0 minus 10 times A over 200. And we can simplify this, cancel the 10, cancel the 0 there, and just write it as dA dt equals negative A over 20 to make it a little bit cleaner. Okay, so after all that is said and done, here's the differential equation. This is all sort of set up stuff that we've done before, and what we're left with is a linear differential equation. This one is also one that's possible to be solved either as a separable equation. I could divide both sides by A, multiply both sides by dt. It is also, again, linear, as I've mentioned, so we could use integrating factor. Whichever method you are more comfortable with. If you encounter a problem that can be solved multiple ways, pick whichever one's easier. So I'm going to write this as a separable equation. So for me, I think that's probably a little bit easier. I'm going to write it as dA over A. So divide both sides by A, and then multiply both sides by dt. And we'll get negative 1/20 times dt. And we'll integrate both sides. And on the left, we will get the natural log of the absolute value of A. And on the right, we will get negative t over 20 plus some constant of integration, call C1. We'll get rid of that natural log by taking e to both sides. So I'll have e to the natural log of the absolute value of A equals e to the negative t over 20 plus C1. make all the arguments about dropping the absolute value and all of that. Let me do that all in one fell swoop. We wind up with A equals some new constant C2 times e to the negative t over 20. So here is our setup up here. Here's the solution down here. We have one unknown, and that one unknown can be solved for by using our initial condition. Our initial condition is written right here. So if I were to rewrite back up with the equation, what is the corresponding initial condition? The initial condition is that the amount of salt at time 0 was 50 pounds. And so we can plug that in. So if A of 0 equals 50, what that tells me when I plug it into the equation is that I'm going to get 50 when I plug in t equals 0. So C2e to the negative 0 over 20. This exponent just becomes 0. E to the 0 is just 1. So what is C2? It is the initial amount of salt in the tank anyways. So C2 is 50, and it again has units of pounds. So our solution is that A of t is equal to 50 times e to the negative t over 20. You plug in a value of time, 10 minutes say, and this will spit out the amount of salt remaining in the tank at that time. Okay. One other type of problem that we might encounter that can complicate things here, and so let's do a more complicated version of this. What if the rate in and the rate out differ? And we saw some problems like this in the homework. You set some up in this way, but we never solved them. So if the rate in and the rate out are different, then the volume of liquid in the tank isn't going to be a constant anymore. And we'll in fact have to come up with an equation for how the volume in the tank is changing. So let's say basically, let's do a second example. Let's do the exact same problem, but let's just change it so that the rate out is 5 gallons per minute or something like that. And maybe we can change the input rate or the input concentration. So let's just say if we have the same equation, as above, but we change two things. I'm going to change R out, no longer 10 gallons per minute, it's going to be 5 gallons per minute. And let's also change the concentration in. Instead of pumping in pure water with 0 pounds per gallon, let's pump in something that has 2 pounds per gallon. Okay, but everything else will stay the same. Same initial condition, same input rate, all of that good stuff. So all we're going to do is have the same starting point. dA dt equals, again, it's always going to be the rate in times the concentration in minus the rate out times the concentration out. And we need to think about each of these pieces. So the rate in, I'm going to say it was the same as the previous problem, so it's 10 gallons per minute. The concentration in, we just changed. It's now 2, and it's going to have units of pounds per gallon. And from that, we're going to be subtracting the rate out, which is now 5 gallons per minute. Per minute. And this concentration is going to be tricky. It's just like this one up here. It's going to be the amount divided by the volume of liquid in the tank, but the volume of liquid in the tank is no longer a constant. It's not going to just be 200 anymore. So this is still going to be A over V, but this V is now a function of time. So let's find VT, and this has units, the same units of concentration, pounds per gallon. So let's find V of T. So let's have that be our first step. So what we know is that the initial volume in the tank, presuming we're copying the stuff from up here, so it started off with 200 gallons in the tank. The rate at that liquid's coming in is at 10 gallons per minute, but it's only going out at 5 gallons per minute. So what is happening to the volume in the tank? Should it be increasing or decreasing? Well, if we got more coming in, 10 gallons per minute, than is leaving, 5 gallons per minute, the volume in the tank should be increasing. So let's presume that there's some extra room in the tank for the water level to rise in the tank. And how fast is it going to be rising? How big or how quickly is the volume of the tank increasing? Well, that is our goal right here. So we know that it should be increasing. We know that at time 0, it has 200 gallons in it. And after 1 minute, 10 more gallons will have been pumped in, but only 5 gallons would have been pumped out. So we should see a net change in volume of 5 additional gallons should have been added in that first minute. And then in the second minute, we would have 20 total gallons in and 10 gallons out, right? After 2 minutes of pumping in at 10 gallons a minute and 2 minutes of pumping it out at 5 gallons a minute, we'd have had a total of 20 in and 10 out. And so we'd be up to 10 additional gallons after 2 minutes. And what we'd see is basically every single minute, we're going to be adding 5 gallons. So V of T should start at 200, and we should be adding 5 gallons per minute. And if we think about the units here, this has units of gallons. This 5 here, so this needs to be the minutes, T has units of minutes. And what is this 5? Well, it's the rate of change of the volume. So it's how many additional gallons are being pumped in every single minute. And if we know every single minute 10 are coming in and 5 are going out, the net change, the net difference between those, so this 5 is basically saying 10 in minus 5 out. That's where we get that 5 from. And it's coming in with units of, again, gallons per minute. And in this case, the minutes would cancel. We'd get gallons plus gallons, which is the units we want for our volume. So this is the equation that we will plug in for our V of T right here. And so our equation is dA dt equals our rate in times our concentration in is going to be, so let's drop the units while we do this portion of the math. We can always come back to the units if we get stuck on anything. But it's 10 times 2. So we're going to have, that first number is going to be 20. And then we're going to subtract 5 times A over V. So minus 5 times A over our V. And we just found our V is 200 plus 5T. So this is our big ugly equation. It is definitely not as nice as the one that we were just doing. It's certainly not as simple. Keep in mind that this equation will only be valid, this model is only valid as long as there's additional room in the tank, that it doesn't eventually, overflow. So if there's only, 200 additional or 200 gallons worth of additional room at time 0, once we fill up those additional 200 gallons, which would take 5 gallons a minute, that should take, 40 minutes? After that, the tank's going to overflow and our model is no longer valid. So just keep that in the back of your mind as well. There are some restrictions on this model, but this is the model that we've got set up. Notice it's still linear, right? The ugly part down here, the part that's showing up in the denominator, is T, not A. It is linear in A. So this is a linear equation, but it's not nice and separable anymore. At least I don't see an immediate way to separate things, right? I could try to divide both sides by, maybe, I don't know. Maybe I could subtract. Yeah, I don't know. I don't see a way to separate it. So not even going to try, but it is linear. So we could use integrating factor on this thing. To use integrating factor, we need to get it in the right form, and that form is dA dt with a leading coefficient of a 1 out here, plus or minus whatever term is proportional to the a. So for us, we would have to move that term over from the right to the left, and that would involve flipping the sign. So I'd have to add 5a over 200 plus 5t. So I'd get 5 in the numerator, 200 plus 5t in the denominator, times a, and that would be equal to 20. This would be my p of t, and my integrating factor, mu of t, would be equal to, so let me write that, our integrating factor, if I can write integrating factor, which is mu of t, is going to be e to the integral of this times dt. So e to the integral of 5 over 200 plus 5t dt. This thing is ugly, but not terrible. You could basically do this with, again, another u substitution, and we could go from there. But we just have one additional problem that I want to do, so maybe I will leave this here for now. Maybe we can finish solving for the integrating factor. What the heck? Let's just do it. Let's go through this problem. So let's do a u substitution to figure out this integral over here. What I would do is let u be equal to our whole denominator there, so 200 plus 5t. What is du then? When we take the derivative, I would simply get 5 dt, which is kind of nice. I've already got that 5 sitting there, so here's my 5 dt. There's my du over u. What's the integral of du over u? So this becomes the e to the integral of du over u. Well, that's going to be e to the natural log of the absolute value of u, which is simply the absolute value of u. What is the absolute value of u? It is this term here, 200 plus 5t, which we know is going to be positive anyways, because we're assuming this whole thing starts at t equals 0, and this number is going to remain positive indefinitely anyways. So we get that mu of t is going to simply be equal to absolute value of u, which is 200 plus 5t. Whoa. There's my integrating factor. If we come back to the original equation, the presumption is then that what I would get is 200 plus 5t times dA dt plus 5 over 200 plus 5t times our integrating factor, 200 plus 5t times a will equal the right-hand side times our integrating factor, so 200 plus 5t times 20. And over here on the left-hand side, this term in the denominator will cancel this term in the numerator, and indeed, you can see that if this is our first function and the derivative of the second, here is our second, and what's the derivative of this first function? We should just get a 5 out of it, and indeed, there is our 5. So the left-hand side looks like the result of taking the time derivative of 200 plus 5t times a. And the right-hand side is that ugly mess that we could just distribute the 20 through, and we would get, what, 4,000 plus 100t? Cool. And we'd integrate both sides with respect to t. And after integrating both sides with respect to t on the left, we just have simply 200 plus 5t times a. And on the right-hand side, what are we going to get? I'm going to get 4,000t plus 50t squared plus some unknown constant c1. And after it's all said and done, a will be equal to the right-hand side, 4,000t plus 50t squared plus whatever that constant is, divided by 200 plus 5t. So a big, ugly rational function. And we'd plug in our initial condition, which was, I don't even remember at this point, I think 50 pounds? Yeah, a of 0 equals 50. So if we plug in a of 0 equals 50, and what we would get is that 50 is equal to, plugging in 0 in place of all the t's, that term will go to 0, that term will go to 0, that term will go to 0, and we'll just be left with C1 over the 200. So what does C1 need to be? I get my zeros right, so we're going to get at 10,000. I think is correct. Yeah, 10,000. And the solution is, after this, it's all said and done for this big ugly problem, is that a of t, let's write it cleanly, a of t is equal to 4,000t plus 50t squared plus 10,000 divided by 200 plus 5t. And hopefully I didn't screw that up anywhere. And again, this is amount. You should be able to go back and do dimensional analysis on all of these different pieces to make sure that you are getting the correct units. This should ultimately have units of pounds of salt. Okay, let's do one very last example. And that is an example of a model that we didn't actually do before, but just so you can see it now, carbon dating. Which should be like a Tinder for nerds or something like that. Okay, so carbon dating in actuality is using the amount of radioactive carbon-14 isotope in various materials to estimate how old that material is. Basically, the isotope of carbon-14 in living material starts to decay upon death of whatever that organic material is. And based on the known half-life of carbon-14, which is like 5,000 plus years, I don't know, I'll look up the number in a minute, you can estimate how old a given fossilized piece of organic material is. Okay, so let me just write this out briefly. The amount of carbon-14, which I'm not a chemist, I'm going to do a dash. I don't think there's a dash. There's probably not a dash. Maybe there's a dash. Don't correct me if you're a chemist or chemical engineer. But the amount of carbon-14 in any organic matter decreases. And it decreases at a rate proportional to the current amount. And this is essentially how all radioactive materials behave. They decay at a rate proportional to the current amount. Okay. So the current amount left. The half-life, so the amount of time that it takes for the carbon-14 to decrease by half also known as the half-life, is 5,730 years, approximately. Okay, so essentially what we've got is, again, let's call it dA dt. This is the rate of change of the amount of carbon-14 as a function of time. So dA dt, carbon-14 per time. The rate of change, which we're talking about right here, this rate is proportional to the current amount left. So it's proportional to the current amount that is left. And this value of K depends on the half-life. So for different materials, different radioactive isotopes that decay, they have different half-lives, and that the equation for all of them would look exactly like this. The only difference would be the value of K. So this value of K you'll find when we go through this and solve it. This 5,730 years is going to come into play to allow us to solve for K. So let's use this idea to solve a specific example. So let's do this one. Let me frame this one as a word problem. A fossilized bone of some sort is found to contain, in whatever little sample has been taken, to contain only 0.4% of its original amount of carbon-14. How old is it? Well, what we're going to do is two things. First, we are going to solve the differential equation. The differential equation will have this unknown value K. So in our solution, we'll have this unknown value K, and it'll also have the constants of integration. So we're going to have two unknown values. We need to use the known half-life along with some information about how much carbon-14 is left in order to try to approximate the current age of this material. So we need these pieces of information. So let's give this a shot and see how this goes. Okay, so if this is our equation, we've already solved this exact equation. This was the same equation we solved when we did the population growth. The only difference was we used P instead of A and R instead of K, but the same technique will work. This one is separable, so I can rewrite this as dA over A equals K times dt. We can integrate both sides, get the natural log of the absolute value of A is equal to KT, KT plus some new constant over here. Exponentiate both sides, make the argument about the absolute value not needing to be there, and we will wind up with, after it's all said and done, and if you want to go see the details, just go back and look at that one, some new constant times e to the kt. Okay. Here is our solution, but as we can see, it has two different unknowns. It has k, and it has this unknown constant c2. Both of those we need to basically try to use to eventually solve for t. What we really want is t. So our ultimate goal, we may not find exactly what these values are, but we're going to use the information that's given up here to try to work out all of these different pieces. So let's just say, hypothetically, let's come up with an initial condition. They didn't tell us how much carbon-14 should be in there initially, so let's just make up an amount, and then we can do everything in relation to this made-up amount. So let's just say, hypothetically, let's let the amount of carbon-14 at time 0, right after this creature died. So at that time, it had an amount A0. Then, if that amount is what we use for our initial condition, then basically we can plug that in to our equation over here. We'd get that A0 plugged in for the value of A is going to be equal to C2 times E to the K times 0. And by the same arguments as before, this exponential is just going to be 1, and C2 must be A0. So A2 or C2 is A0. Get all my subscripts right. C2 is A0. So we have that the amount of the carbon-14 at any given time is going to be whatever the initial amount was times e to the kt. Okay, we don't need to know the specific amount because everything can be done in proportion to this specific amount. So let me indicate what I mean. The information about the half-life tells us the following. The info about the half-life tells us something. What does it tell us? Well, it tells us after 5,730 years, we should have half the original amount of carbon-14. So if the original amount was A0, after 5,730 years, we should have A0 divided by 2. So what it's suggesting is our next condition is that if I plug in A of 5,730, it should be A0 divided by 2, half the original amount. And we can use this condition, so use this to solve for the value of k. So that's going to be our goal. Here's the equation. Let's plug this condition in to solve for k. So basically what it's saying is when I plug in 5,730 in place of our lowercase t, the result that this equation should spit out should be the original A0 divided by 2. So it's saying, so if we sub this in, plugging in, we get that after 5,730 years, the amount that's left should be A0 divided by 2. And if we plug that into our equation, so that's the left-hand side, that's this A of t, the amount that's left. On the right-hand side, we have A0 times e to the k times 5,730. And right now, we can cancel our A0s. They're completely gone from the equation. We don't care about those anymore. So let's solve for k. Right now I have that 1/2 equals e to the 5,730k. Let's get rid of the exponential. To do that, I need to take the natural log of both sides. So the natural log of 1/2 is equal to, on the right-hand side, when I take the natural log of that, it'll cancel the e, and I'll just be left with 5,730k. To solve for k, I simply need to divide both sides by that 5,730. I'm going to get the natural log of 1/2 divided by 5,730. So there's our value of k. So we have the following. A of t is going to be whatever the initial amount is times e to the kt, right? Just coming back to this equation. But we've solved for k now. Here's the value of k. So A0 e to the natural log of 1/2 divided by 5,730 times t. So here's our function a of t. The question now is, what is the value of t? So we've found basically our initial condition. We used our initial condition to find the integration, the constant of integration, and we used the half-life to find the value of k. So we've got our equation now, but that's not what the question asked. We want to know how old the bone is. They didn't ask for an equation for the amount of carbon-14. They want to use the amount of carbon-14 to figure out the age. So we need to basically plug into this equation that we found to find t. So we're given the amount A and asked to find corresponding time t that goes with that amount A. Okay, and what is the amount? It was 0.4%, I think. Yes, 0.4% of the original amount. So as a decimal, 0.4% is 0.004 of the original amount, A0. So that's what we're given. At time zero, or sorry, not at time zero, at some unknown time, the amount has decreased to 0.004 times the original amount. And that's equal to A0 times e to the natural log of a half over 5,730 times t. And so here's our equation. The only unknown is t. This a0 can be divided out immediately, and we just need to solve for the value of t that corresponds to this amount. And so to do that, to isolate t, first thing I need to do is get rid of the exponential. How do you get rid of the exponential? Take the natural log of both sides. So we'll have the natural log of 0.004 equals the natural log of the e will cancel, and we'll be left with the natural log of a half divided by 5,730 times t. And then how do we solve for t in this case? Well, all we need to do is basically divide by this term here, or you can think of that as just multiplying by the reciprocal. So we will get that t is equal to let's write it out this way, 5,730 in the numerator over the natural log of a half in the denominator times the natural log of 0.004. And you can play around with log rules and stuff to simplify this, but at the end of the day, I don't want an answer that looks like this. I want to know an age in years, presumably. So let's figure out how old this thing is. I want an answer in terms of years. What that means is we should be plugging in to a calculator. Let's get a decimal answer. So there we go. Let me clear this again. And let's plug this into the calculator. So I've got, what, 5,730 divided by the log of a half. Log of, I'll just do 0.5. Save myself a little typing. Times, whole thing times the log of 0.004. And when I hit enter, boom, what do we get? This is approximately 45,000 years, 45,643.94, whatever, doesn't matter, years. It's not quite that accurate. You probably can't get this number to be super perfectly accurate, but it'll give us a ballpark answer. And so as far as we're concerned, it's looking like about 45,000 years or so, 46,000 years. So that is our approach. Just to summarize, if we come back to this whole, try to get the whole problem on the screen at once, they didn't give us much information to go with at the beginning, and so we kind of had to improvise. We have our solution, which isn't that hard to find, but we had to pick our own initial condition. And the nice thing is, because we're talking about proportions of the original amount, a half-life is a proportion of the original amount, 0.4% of the original amount. The initial condition doesn't matter because it cancels out of every calculation that winds up mattering. So we'll use the half-life to solve for the unknown value k. We use a made-up initial condition right here to solve for our C2 in the equation because that's the term that doesn't matter. And then we'll use this prescribed amount at the very end to solve for the t, the value of time that is supposedly passed for us to be able to date this particular fossil. So just keep this in mind. We're going to use conditions to solve for unknowns, but the question might not just ask for give me the equation that we've got here. They may ask for you to now apply this equation in some way or another to answer a practical question. In this case, how old is the fossilized bone? So I know we didn't do the carbon dating type problems back in section 1.3, but you may see it here. It's not any harder to do than any of the other problems that we've been doing, and it's certainly one other cool way that some of these problems can be used. So hopefully this will help you get through this homework. I will do our next video on the models that we've encountered that are nonlinear, and there aren't many yet. So it'll be luckily a much shorter video, but the next video will focus on nonlinear models.